Morning, everyone. Welcome to this webinar series 2025 on rate splitting multiple access or RSMAs. I think this is our fourth seasons of RSMA webinar series. This is a special interest group that we have as part of IEEE Communication Societies on rate splitting multiple access. And today we have the pleasure to have Professor Dusit Niyato from NTU in Singapore, who will be talking about the use of AI and RSMA for future communication systems. So Dusit is a president chair in NTU in Singapore, is very active in our community. He's been serving as an editor for many journals, but also as an editor-in-chief for many journals, more recently for transactions on network science and engineering. And he was the past EIC for the well-known IEEE communication surveys and tutorials. Is been a member of at large of the board to the board of governors of IEEE Communication Societies. Is a highly cited researcher with many awarded papers, and is a fellow of IEEE and IET. So before I give the floor to Dusit, let me remind you some very basic rules for this webinar. The talk will be about 50 minutes long and the audience will be muted. You can type your questions within the chat, and at the end of the webinar, we'll have about 10 minutes for Q&A, where audience will be unmuted. We will try to unmute as many people as possible. And you can raise your hands if you have any questions to ask. Enjoy the talk, and I leave the floor to Dusit. Thank you very much. So let me stop sharing, and Dusit, I think you can share your screen.
Okay, yeah. So you can see my screen, right?
Yes.
Okay. Good morning, everybody, and thank you very much for giving me opportunity to present the research work. So the title of the talk is the Generative AI Enable Matching for 6G Multiple Access. So we have this paper available on arXiv. So if you are interested in, so this is the QR code and the URL to the paper on arXiv. So I think everybody know generative AI. So what is generative AI? Generative AI is the AI algorithm that is able to generate new contents such as text, images, and video. So generative AI learn the pattern and structure from existing data to generate the original and creative output. So we already know that we have several services and application of generative AI for text generation, GPT, DeepSeek, image generation, stable diffusion, Midjourney, DALL-E, video generation, Sora, and Alpha 20, Gen 3 Alpha. So there are many advantages of the generative AI. So we just highlight here that it can provide the efficient data modeling because the generative AI can learn the complex pattern from the large data set, be able to improve the data modeling efficiency. And also it provides the creativity and diversity because the output of generative AI model can create unique original content beyond the rule-based method or traditional AI. So it can provide a high quality generation to produce the highly realistic and detailed output, especially, for example, in image generation. So in our research work, we come up with the basic questions. How can we use generative AI for the mathematical problem, which is called matching? So the contribution of our work is that first, we discuss the basic matching theory, and then we introduce the commonly used generative AI model centered around the goal of matching generation. So those generative AI model include the implementation principle, strength, weaknesses. So this fundamental knowledge review how the generative AI can be used for generating the efficient matching strategy. And then we investigate the applications of matching generation in multiple areas, such as potential drug target prediction, task offloading in vehicular network. We also provide a comprehensive summary and analyze the advantages of generative AI matching method in 6G multiple access scheme. And then we propose an effective matching generation framework based on generative diffusion model. We demonstrate effectiveness through the case study called AI generated content service provider selection problem in RED RSMA enable wireless network. So what is the matching theory? So matching is generally defined as the process where we have multiple parties or player. So these player or party have to be paired together according to a certain rules to achieve an optimal and stable state of the matching. So we can see on the in the figure that we have the uh, players. So the player on the left circle try to be matched with right the player in the right circle. For example, we could have the hospital. So the hospital need to be matched with the uh, doctors. So we can have the one-to-one matching. For example, a boy mating with dating with a girl, or many to many, where there are multiple students and different students will read multiple books. So in this way, we can classify the matching model into three major structure: one-to-one, where each player can only be matched with one player from another group. Many-to-one matching, one group of players can be matched with multiple players from another group, but the latter can only choose one player. Many-to-many, that means each player can be matched with multiple players from another group and vice versa. So there are traditional matching method. For example, stable matching algorithms such as deferred acceptance algorithm, top threading class cycle, and maximal weighted matching. Or it could be the matching method based on the decision making AI algorithm, such as we can use the deep reinforcement learning or DRL to optimize the matching. However, the traditional matching algorithm have a limitation. First, it has a high complexity. When we deal with large scale and highly complex matching problem, the complexity of traditional matching algorithm increase sharply due to the large number of players involved in the matching process. So this makes the real-time solution unattainable. For example, if we have 100 player on each side. So we need to match with 100 player on the other side. So there are too many combinations that we need to explore, and that will take too much complexity. The second limitation is the dependence on the complete information. Traditional method typically assume that the player or the participant in the matching can provide a complete and fixed preference list. However, in practice, the player may struggle to fully express the preference. So in this way, the I may not tell the preference order of the other player in the different group. So this will make the traditional method that rely on the complete information difficult or ineffective to be applied. Also, it has the low exploration and convergence speed, especially the decision making AI such as DRL typically rely on the repeated exploration and feedback for policy optimization. This results in the training process that often require numerous iterations to find a stable matching strategy. So these are the major limitations. So therefore, we would like to explore how to use the generative AI model for matching generation. So there are different generative AI model, and the typical one include generative adversarial network, where it can be effective in learning the complex network topology to generate the high quality matching strategy using the discriminator network. It can produce the diverse matching result for large scale net wireless network and be able to adapt to the dynamic environment condition. We have the variational autoencoder that can optimize the reconstruction loss between the original graph and the reconstructed graph to ensure the good stability and generalization. With this capability, VAE can generate the entire group structure at once to quickly obtain the matching result. We have the transformer, which is very good in large language model. It is able to model the global structure of the graphs based on the self-attention mechanism and be able to capture the complex interaction and matching. It is effective in representing the temporal relationship of nodes and edges in the graph based on the sequential generation. So we already know that transformer is very good for the sequential data such as text. And in fact, we can apply transformer for the matching also. Another one is the generative diffusion model. This is very good in providing the accurate and stable matching result by gradually denoising the noisy graph. So this is the technique that people use in image generation, and it is effective in capture the global structure and relationship in the matching problem. However, each of these generative AI model have the different limitation and consideration that we need to take a look at when we apply them to the graph generation. So there are many applications of the generative AI enable matching. First, it is the target matching in potential drug for COVID-19. So the researcher used the variational autoencoder trying to match the structure of the virus to the structure of the protein that is matched to be eliminate or reduce the symptom. Another application which is closer to the communication is task offloading in vehicular network using the generative diffusion model. Here we need to match between the user, for example, vehicles, to communicate with the base station so that the vehicle or the user can offload the computing data processing task to the most suitable edge server. So the matching can be used for the service provider selection in the metaverse service. Again, this could be based on the generative diffusion model where we have the different multiple edge server and we have the different user. So here we need to match the user to the best edge server so that we achieve the best service quality of service and quality of experience. Many other resource allocation in 6G multiple access can be based on the deep reinforcement learning, and a number of them can be modeled as the matching problems. So we can see that based on the existing application of the generative AI matching, so it is different from the traditional static optimization model because generative AI model can adapt the optimization strategy in the dynamic environment because it can learn from the historical data. This makes the generative AI matching problem algorithm ideal for the real-time application that require fast, high-quality decision. Also, it provides intuitive dependency capturing. Matching problem can be inherently represented as a graph with nodes as the elements, such as tasks, resources, user, and we can have the edges as the relationship. By formulating the model in this way, the generative AI model can provide the visualization and be able to capture the complex dependency that is interpretable and also explainable. Also, it can provide the application for the real world uh, application. So the model can generate graph structure, and by imposing the constraint, we are able to structure the graph to be the matching. And this matching provide a pairing strategy that address the real world constraint and be able to optimize the system performance in the scalable and real-time fashion. So in our work, so we look at the use of the generative AI to solve the matching problem. So there are four major steps here. So the first step is that we have the our initial matching from the left hand side to the right hand side. It could be the user match to the base station. So the algorithm that we develop first will put the random noise and map it to the noisy graph through the one hot encoder. So this is the mechanism that allow us to explore multiple choices of the matching or the graph structure. In the second step, the condition during the denoising step, the noisy graph containing the matching relationship will be used to be the input for the denoising network. So this is the machine learning, the neural network that is able to receive the noisy graph structure and be able to give the output by removing the noise and be able to adjust the pairing structure in such a way that it meets all the constraints and maximize the objective function. So in this way, it is similar to the image generation. That means when we try to generate image, we can generate multiple images simultaneously. So the same when we put the noisy graph into the diffusion model. The diffusion model can generate many options for the matching, and we are able to generate multiple trajectories, which are sampled from the denoising network, which again from the step 2, it is the input, and then we calculate the reward to obtain the sum of gradient for the model parameter updating. And this sum of the gradient will be used to direct the best matching that is able to generate the maximum objective function. In the step number 4, the denoising network, which is iteratively updated, can generate the optimal matching strategy based on the current network environment. So we conducted the case study where we have the setup of the 15 user who have a similar image generation or the data computing requirement, and the server is equipped with the AI model where we call the expert. So the server will integrate the diffusion model for the image generation and our proposed diffusion-based framework for the optimal matching generation. So that means your user would like to execute AI model, for example, to generate the image based on the stable diffusion. So we need to perform the matching from the user to the different edge server that hosts the different AI model where we call expert. So the expert will employ the diffusion model for the image generation for the service. So the final image generated for each user is composed of the output from several specific experts. And here, because the user have the different requirement, so the different expert will be selected to give the best quality of experience for the user. So when the user make a request to generate the image from the server, each expert on the server will be specialized on generating the images based on the preference of the user. So based on this matching, we can see that the user have their own requirement and the expert have their own expertise to provide the services for the user. So the user can organize the structure which expert that they prefer the most to the list, while the expert model can provide the preference which user they can generate the best quality output for the user based on the user requirement and the user preference. So in this way, we are able to use the diffusion enable graph to generate the matching between the user. So if you are interested in the technical detail, we have this paper in the archive. So we show some evaluation result, and we show that by using the generative diffusion model batching, we are able to generate the matching from the user to the edge server to generate the output for AI model better than the traditional model. So there are different research direction where we can employ the multi-objective matching design, where we can explore the design of the diffusion model that adapt to multiple objective loss function by incorporating the trade-off mechanism to balance different performance metrics. For example, it could be the delay, throughput, quality of the output data processing. Efficiency and scalability can be explored further, where how can we make the generate diffusion model more decentralized in such a way that we can deploy on the different devices and be able to scale up the users, the number of the user that we can support. It can be integrated with the interactive learning and human AI collaboration, for example, using the generative AI. So this is the first part of the talk. We also have another extension of this work where we apply the graph diffusion base for the aerial base station deployment and resource allocation for RSMA enable user ultra reliable low latency communication low altitude economy network. So here the low altitude economy network is the next generation of the UAV networking. So it is typically composed of the lightweight, low cost effective, and deployable aerial infrastructure such as the UAV and drone. So these UAV and drone can enable agile and on-demand connectivity services in the scenario where we have the traditional terrestrial network, which may not be able to support the application. For example, sensing, navigation, and localization. So even though we can use the base station to perform the localization of the user, however, if we can use the UAV, we are able to localize or detect the object on the ground more accurately. So this low altitude economy network can support the emergency communication. It can improve the coverage, especially in the rural area. On the other hand, it can help to relieve the hotspot. For example, if the special event happen, so we can deploy the UAV to provide extra capacity to offload the traffic from the ground user. So the UAV can be used for the data sensing, acquisition, and information gathering. So this can be based on the visual data, sensor data that the UAV can fly closer to the sensor, collect the data, and relay the data to the base station on the ground. Or it could be the wireless relay where we have multiple users communicate with each other through multiple UAV. So this low altitude economy network or UAV can support highly congested aerial spectrum environment, be able to provide ultra reliable, low latency communication, and be able to support complex scheduling in the multi-aerial base station deployment. And here we would like to highlight that when we deploy the restricting multiple access, the the UAV can even further improve the performance. So the core idea of the rate splitting multiple access, I think everybody know this already. So we have the common part and private part where we have the flexible interference management, partially decoding the interference and partially treat it as a noise. So I'm not going into the detail, but our work focus on how we use the UAV low altitude economy networking together with the rate splitting multiple access to support multiple services. Again, we have still focus on the diffusion model. We show that we did the survey and discover that most existing study formulate the joint deployment and resource allocation problem in the low altitude economy UAV networking as a non-convex and NP hard problem. This make the problem become challenging for the traditional optimization method to solve them in the dynamic environment. So many researchers use the deep reinforcement learning to be the data-driven alternative method that can adapt to the changing environment. So this deep reinforcement learning can perform the trial and error interaction with the network so that they can explore possible solution and be able to exploit the optimal solution. However, this still suffer from the slow convergence speed and the poor generation when we want to adapt the optimization to the new environment. Again, on the other hand, we can use the generative diffusion model to provide a diverse solution space, provide a strong generalization and faster convergence. So again, this capability is inherited from the image generation. So the idea is that we have the input from the user, for example, to generate the image of the cat. So the idea here is we are able to use the input data, put the noise into the multiple step, and then we perform the noise denoising process. And during this denoising process, we are able to change some pattern in the data. So in this way, we are able to generate different images with the different pattern and different behavior in the data, which is similar the first part of my talk, that we can change the structure of the meshing. But here we can do it for the optimization. So motivated by the coordinate interference in the multi-aerial base station network, we adopt the RSMA technology to mitigate the interference to provide the flexible resource allocation and power splitting strategy. So we propose the use of the RSMA enable low altitude economy UAV networking framework with multiple aerial base station. This aerial base station share the spectrum to support the ultra reliable low latency communication services. It is be able to jointly optimize the deployment, association, and resource allocation. The objective here is to maximize the sum rate and the coverage under the power constraint. Here we developed a novel generative AI driven optimization algorithm, which is called GSGD, to solve this challenging mixed integer nonlinear programming problem. By we formulate the aerial base station deployment and the user association as the graph diffusion problem, and we use the denoising generation mechanism to adapt the matching between the user and the aerial base station. We also adopt the SCA algorithm for the joint beamforming and rate allocation. So the simulation show that this proposed joint uh, algorithm outperform the existing decision-based AI baseline in terms of the sum rate, coverage, and convergence. So different from the traditional baseline that they have a limited exploration capability and global information utilization. Our scheme be able to perform the denoising driven exploration that provide a higher reward. And when we combine with the respecting multiple access, it can significantly improve the performance over the other multiple access. Now we look at the system model where we have the location of each base station, the collision between the aerial base station have to be avoided, where we define the constraint that the location of the different uh, aerial base station have to be larger than the minimum distance. Here, the user is served by only single aerial base station, and each aerial base station can serve at least two ground user. So these are the constraints that we impose into the optimization. So we can see that the user is eligible to be served by the aerial base station when it located within the distance of the aerial base station. So that means it's not all the matching that can happen, but it could be the clustering problem. Of course, there could be the overlapping that single user can be served by multiple aerial base station, and this need to be done by the selection whether the user should go with uh, area base station 1 or the base station K here. So we need to optimize the coverage rate of the system that we want to ensure that the single matching is done here. So for the communication model, we can derive the signal to interference or SINR for the common stream, and then the interference among the area base station can be derived, and the quotient interference power from the other area base station can be derived here. So we want to guarantee that the common stream is decodable to all the ground user. The achievable common rate must satisfy the minimum requirement. The SINR of the private stream have to be constrained also, where this part of the SINR will be calculated and incorporated in the total achievable sum rate, which is optimization objective. So our goal here is to jointly design the deployment, user association, and resource allocation scheme with the objective of maximizing the overall system utility. So in order to do this, we incorporate both the sum rate and the coverage rate. We are aiming to enhance the coverage to enable the network to connect many more users. And at the same time, we increase the sum rate that accelerate the information transfer in this air low altitude economy UAV networking, where we define here the system utility, which is the weighted sum of the coverage rate and also the sum rate of the all user that we can cover. We have the user association constraint. The location of the area base station have to be fixed, and the decoding of the RSMA have to be uh, greater than the certain threshold. Transmission delay and the non-negativity of the decision variable, transmit power budget, and UAV collision avoidance and the communication range. So clearly, this optimization problem is a mixed integer nonlinear programming problem. Again, conventional optimization methods such as deep reinforcement learning often suffer from the slow convergence due to the high computational complexity and complex exploration process. And it we need more efficient solution strategy to optimize and solve this problem. Therefore, we propose the joint uh, SCA and graph diffusion optimization problem that be able to solve the original optimization problem. We first decompose the problem into two subproblems, including the beamforming and common rate control. And the second subproblem is for the joint aerial base station deployment and the user association. So here from the left-hand side, we can see that there are uh, the original large problem. So we decompose the problem by using the beamforming and common rate control, and another subproblem which is the deployment and the user association. So we can see that the first subproblem involved the continuous variable, while the second one involved the discrete decision variable. And therefore, we are able to use the graph diffusion model for the deployment and the user association. So for the second subproblem, we represent the network state as the graph where the vertices uh, represent the deployment of the aerial base station, and the edges uh, is represented by the adjacency matrix, which indicate the user association between the area base station and the ground user. Therefore, this subproblem P2 is equivalently transformed into finding an optimal initial matching or G0 that satisfy the given condition. So that is how they choose the matching for the aerial base station. So in our algorithm, we use the graph diffusion process to explore the solution. Again, because it is the generative AI, it can explore multiple solutions simultaneously instead of exploring single solution slowly based on the exploration and exploitation. After we try to explore the different options or the solution, we employ the graph denoising process here to meet to find the solution that meet all the constraints and be able to generate the graph that maximize the objective function. Even though we are formulating the problems as the graph generation, but we are still able to model the graph denoising process as the Markov decision process that we can use the denoising network to replace the actor critique network in the traditional deep reinforcement learning. So we define the expected reward and policy gradient, and we use the Monte Carlo sampling and the eager policy gradient to obtain the different options for the exploration. And we define the reward function as the combination of the different loss function in the network. So for the overall algorithm, here where the environment interact with the graph diffusion, and we have the uh, SCA module that optimize the continuous variable. So the diffusion module, we use this FILM-based graph transformer to denoise the one-hot encoded graph for the aerial base station deployment and the ground user association. So the features here pass through the multi-layer perceptron network and cross-feature attention, and then we have the condition modulation that impose the constraint into the network. And the residue and the normalization will be applied to ensure the stable training. The node and edge state are predicted via the multi-layer perceptron head, and each trajectory that we try to generate the different graph for the network is scored by the reward function. So that means we can evaluate the effectiveness of the trajectory, which equivalent to maximizing the reward function. This will enable the end-to-end policy gradient training. So this is the structure of the proposed framework where we have the original problem of the RSMA UAV matching and power control decomposed into the two options and two sub-problems. And the sub-problem which is very hard to solve, that is the base station deployment and user association, is solved based on the graph generation using the diffusion model. So we have the detail of the algorithm provided in the paper. So the idea here is that we have the initial denoising network parameter, formulation of the Markov decision process, the denoising step, trajectory sample, reward signal, and then we repeat the process iteratively, trying to sample the different noisy graph from the Markov decision process that we choose to connect the ground user to the area base station and also the visible location of the ground user. And then we follow the the standard step of the generative diffusion model by trying to denoise based on the multi-layer perceptron network that is able to generate the different graph. But during that, we also evaluate the gradient and the reward function so that we are able to control the trajectory that maximize the reward function. So we compare with the different approaches, and we are able to show that our approach can achieve significantly higher reward and faster convergence compared with the deep reinforcement learning. So we are able to, one insight is that we are able to increase the number of denoising steps to improve the reward performance. However, at a certain point, the reward improvement becomes stagnant, and we found that 15 step of the denoising will provide already the good trade-off between the performance optimality in terms of the accuracy and computational cost. So this is insight that we can leverage, because later if we need to perform the generalization of the model, we already know that we do not need to compute or iterate for the solution beyond 15 steps, because that will not give much more improvement to the reward function. And this is also uh, similar to the learning rate, that we can achieve the optimal or the best learning rate for one situation that provide the best balance between the convergence speed and the final reward. Again, this is good for the generalization when we want to apply the model to the different environment or model. So here the framework can, yeah, we can show that during the different step of the denoising or exploration, so the matching between the aerial base station and the user keep changing, and eventually it will become stable. Even we increase more uh, iteration or the denoising step, the reward will not be further improved. So this is the benefit of using the generative diffusion model. So we can see that it is robust to the different parameter variation. For example, if we vary the number of area base station, so the performance can be still better than the baseline. And we can show that when we compare with the in terms of the number of ground user and also the communication range, our scheme perform the best in terms of the reward function or system utility that we want to maximize the sum rate and the coverage rate. Okay, so that's my talk today, and if you have any question, please let me know. Thank you again.
Thank you very much, Tao, for these very interesting talks. We have about 15 minutes, so
Yep.
we're going to open the floor to questions. If you have any questions, please feel free to raise your hand.
Yes, please.
Sibo, do you see any questions so far?
There's one in the chat box.
Yep.
How to correlate capacity and coverage parameters in generative AI environment.
Okay. So okay, I think this is the second part of the talk. Okay. So so we in again, so this is the weighted sum of the coverage rate and the sum rate. So the idea here is that we can impose this system utility when we uh, train the model. So that means here we can impose the objective function into the denoising step. And during the trajectory optimization, that we select the trajectory based on the deep reinforcement learning. So we are able to incorporate that reward function. So this is the reward function that we calculate based on the sample of the trajectory that we have in the matching or graph generation. So that is how the coverage rate and also the sum rate are incorporated during the denoising step in the graph diffusion model. So again, if you are interested in the technical details, so this equation and derivation will precisely show how the reward function can be incorporated during the sampling and the trajectory control of the diffusion process.
Thank you, Tao.
Yeah, you're welcome.
So I noticed you use these generative AI or diffusion models in the assignment problems, right?
Right.
I
Yeah,
was
which is
yeah.
yeah.
Do you think you can use this also at the physical layer? So you use the SCA at the physical layer. What prevents you
Yes.
from using that at the physical layer for the whole beamforming and RSMA optimization?
Okay, yeah. Thank you very much for this. A good point. So in fact, we try to address the problem which is harder to solve because the discrete optimization is always a headache for the networking people. So that's why we try to use the generative AI to address this issue. We have some work that we use the diffusion model to optimize the continuous optimization problem. And we're still exploring this, that it could be a future work because, for example, the SCA, we know that is is quite efficient already, but still the successive convex optimization approximation still have a limitation that it need the precise and parameter uh, to be known before we solve it. So this we still working on how to uh, relax this assumption. For example, if we don't have a complete information, how can we use the diffusion model to explore the data distribution so that we can replace the SCA by the diffusion process to generate the continuous decision variable. So my answer is that yeah, so this diffusion model is quite good for the uh, discrete optimization problem, but for the continuous optimization problem, we still need to explore further, study further.
Very good. Okay.
Yeah, thank you.
Any other questions? I have many questions, so but I would like to leave the floor to others. If no other questions, then I will ask you another question, Tao.
Yeah,
I was
please.
wondering, can you use those diffusion models or generative AI to discover new multiple access? So in the same way as this has been used in other fields where you can discover maybe new molecules.
Exactly.
Can you discover new multiple access schemes that goes beyond RSMA?
Okay, so yeah, actually this is a very visionary question. So we have not explored this the question yet, but I think is I think many researchers already try to use this. For example, they try to use the diffusion model to generate the new channel coding. So in fact, the result is quite fascinating because they can use the transformer, which is good for the sequence data, sequential data, like a text, to generate the source coding. Uh, yeah, channel coding. Sorry, channel coding to match with the unpredictable channel condition. So this is the existing work that the many researchers try to explore. And I think in the similar spirit, the diffusion model and even transformer can be applied for the new multiple access mechanism, how to do the waveform design and other parameters in the physical layer. So that's for example, even the sequence of the data 0, 1, how can we translate that into the uh, channel coding, we can match with the channel coding in such a way that when we transmit, the bit error rate is minimum. So I think this is a very open question.
Very good.
Thank you.
Thank you, Tao.
Yeah, challenging question actually.
Yeah, I mean, it's always the questions I was wondering, because it's been used in many fields, right, to discover new stuff. So I was wondering always,
Yeah,
because this
that's
is
true.
one actually of the area that we have in one of our paper on multiple access in the proceeding of IEEE, where we say that there may be the potential to build based on RSMA that already unified various multiple access like SDMA and NOMA and physical layer multicasting, a particular instance of RSMA. And maybe there is a way to go towards a more universal multiple access that encompass and plays with all possible dimensions that we have. So time, frequency, space, power, signal domains, code domains, all those different dimensions would be captured within one universal multiple access. But how to generate this universal multiple access is not easy. And so that's why I'm wondering whether your approach there using generative AI could potentially shed the lights on how you actually generate this universal multiple access that would unify everything.
Yeah. So yeah, this is a good question because we already see that the AlphaFold, for example, for the protein structure prediction. So that's from the DNA sequencing. So that's a very effective, and now they even claim that is accuracy is more than 80-90%. So one day we can generate the new multiple access that 90% accurate for the unpredictable channel condition. So that's a very interesting question.
Excellent.
Thank you.
Okay. Any other questions? Anyone online?
Yeah, please.
I don't see any other questions so far. So I think we're going to stop here then. Thank you again, Tao, for the excellent talk. Thank you for contributing to this webinar. And our next speakers will be, I'm not sure, Sibo, maybe you know, will be our next speaker. And when, I think it's probably in a few weeks from now. Let me check. So our next speaker will be Jin-Suk Choi from KAIST in September. So we'll have a break now in July and August, and we'll resume the webinar series in September with Jin-Suk Choi. And we'll have a few other speakers in September. Okay, thank you very much, everyone. Thank you, Sibo. Thank you, Tao, again for the great talk. Thank you, everyone online for attending. And see you at our next webinar.
Thank you. Bye-bye now.
Thank you. Bye-bye.
Bye-bye.